We've talked about sequences, and we've talked about the idea that each sequence has a term in order. You have the first term, the second term, the third term, and the fourth term. And we've talked about the idea of the limit of a sequence. So we can examine the sequence terms as they go towards the largest, or not really the largest, but towards infinity, or towards an infinite number of terms, and see what happens. But now we want to talk about something called a series. So if I've got a sequence that's got the first term, the second term, and the third term, what I'm going to do is I'm actually going to construct or define a separate sequence, and I'm going to call this sequence S. So if this is A, it's the sequence of A, this is the sequence S. And a lot of times you say AN or SN. Where the first term of this sequence is just the first term of the original one, but the second term of this sequence is the first term plus the second one. The third term is the first plus the second plus the third. And hopefully you can see that if we go down to some arbitrary term, what it's really saying is that this sequence is the sum of the number of terms. So it's keeping track of how many terms you're summing up. So for instance, the 10th term here is the first 10 terms added together. And so you might ask yourself a question, why would we want to do this? And one of the reasons we like to do this is that we might know, for instance, that a sequence converges to 0. But we might want to know if it converges so quickly to 0, whether or not those terms, when you add up them all together, if that still converges, maybe not to 0, but if that still converges to some number. And this has a strong analog with the idea of improper integrals. If you think about improper integral, we have a function and we want to integrate it all the way out to infinity. But if that function doesn't go to 0, there's no way that the integral is going to converge. And then on top of that, just because it goes to 0 doesn't mean that the integral doesn't push off to infinity as well. Anyway, but the idea is ultimately these have these terms, and these are what are called partial sums, because we haven't summed all of the sequence together. We've summed just a part of it, the first, just the second, first and second, just the first 3, just the first n terms. And another way to write that is this shorthand, from k equals 1 to n of a k. So hopefully you recall that sort of notation, that sort of summation notation from introductory calculus or maybe even pre-calculus. And this just simply says, using this index, start at 1, make your way up to n, and add all those together. So then what we have is, if we have this term, then there's a secondary expression where instead of n, it's actually infinity. And in that particular case, what we're describing is not only a partial sum of a finite number of terms, but we're actually taking that all the way out to an infinite number of terms and defining the sum, or sort of like that final expression of what it all adds up to. And this expression here, not so much the s, but that expression is called an infinite series. I also want to note real quickly that notice that for this sequence, you can also always define it recursively. It's each term of the sequence is the previous term plus the corresponding term in the A sequence. So if you look at here, S3 is S2 plus A3. So those indices match, and then this right here is just S2. So we can define it recursively. The reason why that's sometimes useful is that if we can get an expression for n, we can kind of see how adding a little bit to it affects that sum. That can be useful at times, not often, but it can be. Now, there's a kind of an important piece here, which is that if the sequence converges, then S converges, and they're really kind of the same thing. Essentially saying that if this sequence converges to a value, so if it doesn't blow off to infinity, then we say that the infinite series converges, and so we can so it's useful because then we can talk about this or talk about that equivalently. And we're going to play with that as we start looking at functions long term when we talk about Taylor's theorem and other expressions involving infinite series. It would be nice to be able to deal with both of those. Sorry, I said Taylor's theorem, I meant Taylor's series. Taylor's theorem is related but not directly there. So let's take a look at a specific example. If the sequence is 1 over 2 to the n, then by definition, if the A sequence is this, the S sequence is the sum from k equals 1 to n of those terms. And if we look at that explicitly, we say, okay, the first term is just the first term of A, so that's 1/2. Now the second term is 1 over 2 to the 1 plus 1 over 2 squared, so that's 1/2 plus 1/4, which is 3/4. Now the third term is 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed, so 1/2, 1/4, 1/8, which is 7/8. But another way to represent this, a more convenient way to represent this sequence, is like this. If you look at 1/2, it's actually 1 minus 1/2, so it's 1 minus 2 to the first, 1 minus 2 to the second, 1 minus 2 to the third. So this index matches that power. So then I could say that the S-nth term is 1 minus 1 over 2 to the n. Why is that useful? Well, that's useful because I can then take the limit of that sequence. I can say, all right, what's the limit of this as n goes to infinity? Well, this doesn't change because it doesn't depend on n. And when n gets large, 2 to the n gets very large. And so 1 over 2 to the n just sort of disappears. So we say that term disappears as we go to infinity, so the infinite sum is actually 1, which is kind of an interesting result. Because it's saying, okay, if I take half, and then I add up half of what's left, and then I add up half of what's left, and half of what's left, and half of what's left, what do I get, right? So let's kind of take a look at that. I didn't draw this originally, but I want to draw this because this is a really interesting idea. So if I have a 1 by 1 square, so it has total area 1, okay? What I'm going to do is in the first term, I'm going to add up half of what's white, or what's clear, what's not marked. Okay, in the second term, I'm going to add up half of what's left. Right, because I added half, and then I add a half of that half. So I add a half of what's left. And then I add a half of what's left. And then I add a half of what's left. And then a half, and then a half, and then a half. And you can kind of see as I keep adding half of what's left, I never can get outside the bounds of that box because I'm never adding more than half of what's left. So nothing I would do would push me outside that unit square. But each time, right, by the, I don't know, what was this, the 1, 2, 3, 4, 5, 6, 7th, by the 7th term, I only have that little sliver left. And so what I keep seeing is that this little remainder term keeps just shrinking, crushing down to 0. And that's why this converges to 1. So I want you to do, if you're still listening, if you've made it this far, I'd like you to go look up something called Xenos Paradox. Xenos Paradox is a really interesting idea about this exact concept. And it was the idea that, is this actually possible? And it's sort of philosophically debated. But the math is actually pretty clean, right? Well, anyway, blah, 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 blah. The sequence converges to 1. So we could either write this, or we could just say S equals 1. So what I can say is I can use this exact term anytime I would use a 1. Now, you may not always want to do that, but there are actually convenient times that you'd like to do that. Now, there are other perfectly fine sequences where the limit of the sequence is 1, or limit of the sequence is finite, but the limit of the series is definitely not finite. So consider a case where every element was 1. It's just 1, 1, 1, 1, 1. Well, the limit of that sequence is 1, right? That doesn't change. But if we think of the series, well, the first term is 1. The second term, we add another 1, so it's 2. The third term is 3. Fourth term is 4, and so on. So the nth term is n. Well, if I take n to infinity here, it's just going to blow up, right? If I keep giving you $1 every second, all right, or whatever it is, well, eventually that's just going to add up to an infinite amount of dollars. or it's just going to grow immeasurably large. It's definitely not going to converge. It doesn't get smaller, or it doesn't stop happening. So this is a really good example of how you could have a limit or a sequence that converges very, very clearly, but the series also diverges wildly. And we're going to do some examples to give us a little better intuition on how to deal with sequences and series. But what you can see is that really a series is just a sequence, but it sort of has an under the hood definition related to another sequence.